Hello, welcome to the channel. So in this video, we shall start a new series. It is KSET-Jan 2024 detailed solutions. So in this particular video, we will be discussing the first 20 questions, and all these 20 questions, they are from inorganic chemistry. Let's start. Before moving on to the questions, if you want chapter wise as well as topic wise sorted KSET previous questions, you can refer to these books, KSET in Chemical Sciences, in Organic Chemistry as well as in Physical Chemistry. You can contact the number or WhatsApp to get your copies. First question. In this question, they have asked, the highest electronegativity difference is observed in this pair. Actually, it is not a new question, so it is directly taken from KSET 2016 itself, and these kind of questions even they have earlier appeared in CSIR NET examination. So that's how it is always beneficial to solve old questions. So definitely such questions, or sometimes directly questions can be asked or picked from the earlier examinations. So now if we consider this question, if we know the electronegativity of each and every element, then directly we can solve this, but it is very rare that we remember all the electronegativities. But just if we want to refer the electronegativities, so here just I have listed the electronegativities of all the elements in Pauling scale. So lithium, sodium, potassium, alkali metals, and they will be usually having less electronegativity. So that's how, so it's in the range of 1 to 0.8, and of course lithium to sodium and sodium to potassium, it decreases. This fact we know. And two more elements what they have covered here is fluorine as well as chlorine. At least this electronegativity values usually will be knowing. Fluorine, it is more electronegative and the value it is fixed to be 4.0, and relatively the value of chlorine it comes to 3.0. But actually it is not expected from you that you should know these values and from that you should solve this question. So if you know how the electronegativity values vary in the periodic table along the period as well as down the group, from that also it can be calculated, or it can be the question can be answered easily. So how we can do that we shall see. See, now partially I have represented the periodic table. So now starting from lithium, if we go in this direction, we know that the electronegativity increases along the period, and down the group it decreases. This fact we know, right? So from that we can just know that, so this portion or the right hand corner, top corner of periodic table, it is comprising of more electronegative elements, and this left bottom corner, it comprises of elements with relatively less electronegativity, right? So now if we want to identify the elements or pairs with highest electronegativity difference, in that case, for highest electronegativity difference, one element it should be most electronegative, and the other element among the given species it should be less electronegativity, less electronegative. So now from that perspective, if you look at fluorine here, we can easily say that that's the most electronegative element, and among the species, among the given species, less electronegative species, it will be potassium. So if you consider potassium and fluorine, definitely the electronegativity difference it will be high. So on that basis the question it can be answered, and the answer for this question it will be this option B, K and F. Let's move on to the next question. Second question, it is also a very simple question. Again, it is a repeated question from KSET 2016. So here simply they have asked the correct decreasing order of size. In fact, from 2016 partially the question has been picked. So the same question it had appeared in the 2016, but along with that one more property, decreasing or increasing order they had asked. So here just they have asked decreasing order of size. So how we can do that we shall see. So if you look at these species S2 minus, Cl minus, K plus and Ca2 plus, first thing that should come to our mind is that these four species, they are isoelectronic species. So if you count the number of electrons present in all these four species, that comes to 18. Z I have just given for reference. Z it is different, atomic number is different, but because of the charge here, 16 electrons from sulfur and 2 minus charge, totally it makes 18. Similarly for Cl minus 18 electrons. Even for potassium, atomic number 19 but 1 plus charge, so that means number of electrons it comes to 18. And calcium 2 plus, atomic number 20, the number of electrons it comes to 18 itself. So all these 4 species, they are having just 18 electrons, and that's how they are isoelectronic species. And among isoelectronic species, how the size varies, that we should know. So in the case of isoelectronic species, number of electrons being same, the size mainly it depends on the atomic number. Higher the atomic number, lesser will be the size, or smaller will be the size, because more number of protons, they are controlling 18 electrons. In this case 20 protons, they are controlling 18 electrons, whereas here if you come, the same number of electrons, 18 electrons, they are controlled by just 16 protons, and that's how here nuclear control over the electrons it will be less, because of that size it will be more here, right? So now among the isoelectronic species, directly it can be said that size decreases with decrease in Z effective. So based on Z effective we can give this order. So here it will be very large size due to less Z effective, and here it will be, okay, there is a small correction here. Among the isoelectronic species, size decreases with increase in, this should have been increase. Yeah. So among the isoelectronic species, size decreases with increase in Z effective. So that means when Z effective increases, as it happens in the case of calcium 2 plus, because of more Z effective, size decreases, and the correct order it will be sulfide, chloride, potassium and calcium. So among the given options, it is I think option C. So option C, it is the correct answer for this question. Moving on to the next question. Again, this is a very simple question from molecular orbital theory. Just straight away they have asked the bond order of O2 plus ion. So how we can do that? First we should know the electronic configuration of oxygen atom. It is 1s2, 2s2, 2p4, well known fact. And from this we can go for directly molecular orbital energy level diagram of O2. To start with, we can start from O2. So if you consider O2, you should be knowing this. In the case of O2, when atomic number crosses 7, that is nitrogen, the energy levels or relative positions of pi as well as sigma energy levels, or I can say from O2 onwards it will be like this: sigma 2pz, it will be above pi 2px as well as pi 2py, whereas in nitrogen and other elements below nitrogen, so it will be like sigma 2pz it will be below, and pi 2px and pi 2py it will be above that. So that fact you should know. So now I have already written 4 electrons here and 4 electrons here. So now how we fill these 8 electrons for O2? I am discussing O2. So it will be like 1, 2, 3. 1 second. 1, 2. Then it will be like 3, 4. Then 5, 6, 7 and 8. 4 electrons from this oxygen atom and 4 more electrons from this oxygen atom. Totally it will be 8 electrons. They can be filled in this way. This is for O2. But what they have asked is for O2 plus ion. So which means 1 electron it is to be removed. And if I just decrease 1 electron, say this electron it is removed, in that case we can easily go for calculation of bond order for O2 plus. In fact, it is very simple question. So now bond order it is given by this formula: number of bonded electrons, number of bonding electrons minus number of anti-bonding electrons divided by 2. Of course, I have considered only 2p orbitals because all other 2s as well as 1s it will be filled. So those filled orbitals, they will not contribute towards bond order. So therefore only I have considered this 2p part. Bond order it can be calculated like this also. Or if you want to consider 1s2 and 2s2, in that case also you will get the same bond order. So now if we just apply this here, number of bonding electrons, if you count bonding electrons, it will be here 4 and here 2 more, it will be 6 totally. So it will be 6 minus anti-bonding electrons. If you consider only 1 anti-bonding electron we can find here, and now so that's how it will be 1. So 6 minus 1 divided by 2, so that will be 5 by 2. The bond order will be 2.5, right? So Otherwise also straight away also this can be worked out. If you know that the bond order of oxygen, it is 2. Oxygen, if you talk about oxygen molecule, it will come to 2. And to create O2 plus species, you are removing 1 electron from antibonding. This is pi star, antibonding molecular orbital. So removal of electron, 1 electron from antibonding molecular orbital, that in fact increases the bond order by 0.5. From that factor also you can answer that it is 2.5. Otherwise, if you want to do it systematically, you can do it in this way. Right? So option C, it is the correct answer for this question. Again, the next question, it is also a simple one. Similar kind of questions earlier also they have appeared. Straight away this question, it is about the shape of ClF3 molecule. How we can work out the shape of ClF3 molecule according to the VSEPR theory, that we shall see. So ClF3 molecule, what we need to count is the outer electrons from chlorine as well as the outer electron from fluorine. So Cl, it will be central atom, so all the outer electrons in the valence shell that we should consider. So for fluorine, each fluorine, it is just coming with 1 unpaired electrons, that we can consider. So therefore Cl, it has 7 electrons in valence shell, plus fluorine, each fluorine it will come with 1 electron, totally it will be 3 electrons. So if we take the sum, it will come to 10. And now if once we know total number of electrons which are present in the valence shell of fluorine according to VSEPR theory, we can say that it will make 5 pairs of electrons, and according to VSEPR considerations, 5 pairs of electrons, this should give you TBP geometry, trigonal bipyramidal geometry. So therefore the geometry of this particular molecule, remember I am talking about geometry which is based on the total number of pairs, or this is even called as steric number. Steric number for ClF3, it happens to 5 and it corresponds to TBP shape. So for TBP in VSEPR, for 5 pairs TBP shape, so that is this. And now we need to know even one more fact which is called as Bend's rules. According to Bend's rules, in summary we can just say that whenever electronegative atoms are present, those electronegative atoms those go to axial positions first. According to Bend's considerations, we should send the more electronegative atoms to axial positions first, then we should fill the remaining 5 pairs of electrons. 2 pairs we have consumed here, 1 more pair it will be here. These 3 positions, they are equatorial positions. So now if you look at the statement, easily you can come to the correct conclusion. It has 2 axial lone pairs. No, it has 2 axial fluorine atoms. It has 1 axial and 1 equatorial lone pair. No, both the lone pairs, they are present over equatorial position. It has all fluorines of equal bond length. No, this axial as well as equatorial bond lengths, they will be of a different bond length. Axial, usually it will be elongated one, and this equatorial bond length, it will be relatively shorter. So that's how option C is also wrong. And it has 2 equatorial lone pairs. Yes, that is the correct statement. So in the tentative answer, I guess they had answered this wrongly, but later in the final answers it has been corrected. The correct answer, it will be, it has 2 equatorial lone pairs. VSEPR, it is very, very important, and at least one question you can definitely expect in KSET or any other competitive exam based on VSEPR theory. So therefore you should be very perfect with VSEPR theory. Move on to the next question. This is also very simple one. Even if you do not think into the question, superficially also it is possible to answer this question. Which of the following substance is classified as weak acid? If you look at the species, the basic idea of acid means it should have some protons which can be donated to some other species. From that consideration also, straight away you can say that it should be ammonium, because no other species they have protons associated with them. So therefore from that consideration also, straight away you can say that ammonium, it should be the correct answer for this. But let's see, or let's discuss this question in bit more detail. If you consider these 2 species, NO3 minus as well as ClO4 minus, they are actually produced from corresponding acids. This is from nitric acid. When nitric acid dissociates, it produces H plus as well as nitrate anion. Similarly, if you consider this HClO4 minus ion, HClO4 minus is not necessary here. HClO4, it will produce H plus ion as well as ClO4 minus ion. And So ClO4 minus ion, perchlorate ion, it comes from this HClO4, which is perchloric acid, right? So important thing here is that these two, they are acids, and we know that both of these, they are strong acids. HClO4, again I'm mentioning, minus is not necessary here. This minus charge, it's not necessary here. These HNO3 as well as HClO4 both are strong acids, and when they dissociate, they produce this base, conjugate base, and according to Bronsted-Lowry theory, when the acid is strong, corresponding conjugate base, it will be weak. From that theory, we can identify these to be nitrate as well as perchlorate ion to be weak base. So definitely they are not weak acids, but they are weak bases. So that's how these two, they cannot be the answers. Similarly, if you look at the other species, CO3 2 minus, it can be produced from bicarbonate ion, HCO3 minus ion. When it dissociates, it produces H plus and carbonate ion. Now here also, this species you can consider it to be acid, because this is having one proton which can be donated, and this is actually a weak acid. This will not undergo dissociation that easily. Relatively, this is weak acid, and the corresponding conjugate base, whatever we get, that will happen to be strong base. Strong base in the sense everything it is relative. So like considering this to be weak, relatively this is considered to be strong in that way. So that's how this cannot be the answer. Carbonate is also not the answer. Whereas this species, ammonium ion, if you consider, it can dissociate to produce ammonia as well as H plus ions, and this is also weak acid itself. So like corresponding conjugate base, it will be relatively strong here. So among the four species, given species, the species which we can call it as acid, and that to weak acid, it will be this ammonium. Remember, everything strong and acid, strong and weak acid, it is just a relative. Let's move on to the next question. Again, a simple question. First few questions, maybe some first 10 questions, they were really simple. Identify the protic solvent among the following. So you should just know the structures of these four species, and based on that, if you know which can be identified as protic solvent, easily it can be done. So let's just see the structure. Tetrahydrofuran. So tetrahydrofuran, it has protons. Here it will be CH2, 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 CH2. But those protons, they are not ionizable. They are not easily ionizable, and they are not readily available for donation. Though this THF molecule contains protons, it is not considered as protic solvent, because protic solvent by definition, we should have ionizable protons. Similarly, if you go for dimethyl formamide, here also same thing. Though we have protons, they are not that easily ionizable. So therefore, DMF, it is also not considered as protic solvent. Carbon tetrachloride, it is easy to identify because it does not contain protons at all. So therefore, in no scenario it can be a protic solvent. And last one, HF. HF, yes, it can dissociate to form H plus as well as F minus. So this can dissociate to produce H plus as well as F minus, and that's how it can donate protons, or it has ionizable protons. So therefore, among the following solvents, the protic solvent, if it is asked, we should go with hydrofluoric acid, HF. That is the answer. Next question. It is based on the structure of oleum. Different kinds of acids which are derived from sulfur they have given. Among this, which is oleum, that is to be identified. In fact, it is very easy. If instead of oleum, if they had asked about any other species which they have given, like H2SO5 or H2S2O8, then it could have been difficult. But usually we study oleum, and oleum formula, it is H2S2O7. Straight away it can be identified. But we shall see structures of all the four species that they have given. First one, it is very easy, sulfuric acid, structure of which is represented here. So that the next one, H2SO5, just one more oxygen it is present extra in comparison with the sulfuric acid. Such sulfuric acid, it is called as persulfuric acid, and the extra oxygen atom, it will be inserted here between sulfur and oxygen. So this will be persulfuric acid. Whereas H2S2O7, which is known as a disulfuric acid, or that itself is known as oleum. So here, in fact, even it is like H2SO4 in contact with SO3. Very strong H2SO4, fuming sulfuric acid. When it has sufficient SO3, it can form this kind of species. That SO3, it gets inserted in between S and O. So therefore, for such sulfuric acid, it is called as disulfuric acid, because you can see both two sulfur units they are present here. So such sulfuric acid, it is called as disulfuric acid, or even it is called as polyamine. The fourth one, D option, it is H2S2OA. So compared to this, it has one more oxygen atom. So that oxygen atom, it is inserted here. In between two sulfur atoms, it will be inserted, and it will be called as peroxysulfuric acid. And formula of peroxysulfuric acid, if you consider, it happens to be H2S2O8. And it is very important to remember all these structures and related structures and some more other acids and their structures. Questions can be asked from any corner. So now straight away we can say that the answer for this question, it will be option C, H2S2O7. Right. So the next one, it is from environmental chemistry actually. Which compound gives photochemical smog as brownish color? First thing that we should know is that photochemical smog, one of the constituent which can help in forming photochemical smog, it is oxygens of nitrogen. But if you consider here all the options, they have given it as nitrogen oxides itself. Among this, the most important one, if we have to pick, it is said that it is NO2 which is mainly responsible for the formation as well as the brownish color of photochemical smog. Otherwise also NO2, whenever we use nitric acid as a reducing agent, one of the product, it will be NO2 which will be produced as a brownish gas, LO2 brownish gas. From that perspective also, it can be guessed that it should be A. Photochemical smog, it is mixture of pollutants that are formed when nitrogen oxides, mainly nitrogen dioxide NO2, and volatile organic compounds, when they react in sunlight, they produce a brown haze, and that is called as photochemical smog. And the answer for this, it is NO2. In fact, if you look at the reaction series of reactions, so this NO2, when it reacts with sunlight, so the UV light which is present in sunlight, that will break this to NO and O radical, and the further reaction series continues. So from that perspective also, option A, it is the correct answer for this question. The hybridization of sulfur in sulfuric acid. Very simple. If you know how you can identify the shape of the molecule. So the shape of this molecule, in the earlier slide we have discussed sulfuric acid, its structure we had discussed. Actually it is a tetrahedral shape, and if you just know the fact that it is tetrahedral, so from that itself easily you can say that tetrahedral always it corresponds to sp3 hybridization. So the hybridization, it will be sp3. But if you want to look at the things in more detail, sulfur electronic configuration, it is represented here. It will be 3s2 3p4. It is below oxygen, so therefore oxygen is 2s2 2p4. This will be 3s2 3p4. Now when sulfur it undergoes sp3 hybridization, this s orbital it combines with this p orbital, and what happens is that 4 new hybrid orbitals are formed. And now if you consider here, totally 6 electrons are present. So out of those 6, 4 electrons it is considered to be occupied here in sp3 orbitals according to valence bond theory approach, valence bond structure of sulfuric acid, and 2 more electrons they occupy the next energy level, that is 3d. So now further, these 4 hybrid orbitals, they form 4 sigma bonds with 4 oxygen atoms, as you can see. In fact, those sigma bonds, they will be deciding the geometry as well as shape of the molecule, because sigma bonds, they are directional, and these 4 sp3 orbitals which make 4 sigma bonds in tetrahedral manner, that gives tetrahedral shape to the sulfuric acid molecule. But if you look at in sulfuric acid, you can have pi bonds also. Those pi bonds, they are formed between oxygen and the electrons which are occupied in 3d levels according to valence bond approach. So ultimately the hybridization, it is said to be sp3 itself. So therefore sp3, option C, it is the correct answer for the question. Again, straight away question, factual question. What is the major mineral present in the phosphate rocks? Phosphate rocks, they are even called as rock phosphate or phosphite. So it is actually calcium phosphate based mineral. So even if you just know that fact, it is calcium phosphate based. So here it is nitrogen phosphate. Here again, sorry, not nitrogen, sodium phosphate. Here also it is sodium phosphate related. Here it is calcium chloride and calcium oxychloride related they have given. And here only in option D they have given calcium phosphate. So therefore this should be the answer. Actually, if you look at the phosphate rocks, they are either made up of fluoroapatite. So fluoroapatite formula it is Ca5PO4 thrice F. So if you just consider calcium, it is 2 plus, so it will be 10 plus charge. Phosphate, it will be totally 3 minus, so it will be 9 minus, 3 minus into 3 9 minus plus 1 F minus, totally it is 10 minus. So 10 plus 10 minus, it is balanced. Calcium phosphate, it can be in fluoroapatite form like this, or it can be in one hydroxyapatite form, so it is this. So ultimately it is calcium phosphate, so therefore the answer it should be option D. Questions from coordination chemistry. It starts from 11. Few more questions, they are related to coordination chemistry. Again, this is straightforward question, but definitely there are chances here that you can be confused a bit and you can just go wrong with this question. So carefully this question is to be answered. The crystal field splitting energy for octahedral, it's delta O, and tetrahedral delta T. Often sometimes this is said to be delta 0. It is not actually delta 0. Here also they have written it as delta 0, but actually it is delta O. That is splitting in octahedral. O stands for octahedral there. Yeah, if you look at, so the splitting, relative splitting, it will be of this kind. So if you consider d orbitals, if they form octahedral complex, the splitting it will be more, and the tetrahedral complex, the splitting it will be less. Reasons are that why in case of octahedral complex the splitting is more and here it is less. We shall see those reasons, but first fact that you should know is that octahedral splitting is more as compared to this tetrahedral, because just based on that you can eliminate one of the option here. One of the option, it can be just eliminated on this fact, and even if you end up in confusion just based on this fact that delta O it is larger as compared to delta T, from that fact itself the correct answer it can be identified. And the relationship you must be knowing, it is actually almost half but not exactly half. Even if you know that fact, from that basis you can remove these two options. Essentially these two, they mean the same, right? So based on that, that also you can decide that B and C it could not be the answer, because they essentially mean the same. Delta O is approximately equal to 2 times delta T, or in other words delta T that is equal to half times delta O. Just say 2, if you move it here you will get this equation. So therefore these two, they are not the answers. And now among these two you have to choose the correct one. If you are confused here, 4 by 9 the value it is given correctly, but whether it is delta T which is equal to 4 by 9 times delta O, or delta O which is equal to 4 by 9 times delta T, to decide that this fact it comes to your help. Delta O is always larger, right? So if you look at here, they say that you should reduce this delta T by 4 by 9 times. 4 by 9 means approximately it comes to 0.45 times. So that means that delta T is larger, and if you reduce that delta T by 0.45 times, then you get delta O, right? So in this option they are mentioning that delta T itself is large. That cannot be the possibility, because delta T it is smaller, so you can just decide that this is not the answer, whereas this one it is correct. Delta O is more, and if you just consider just 0.45 portion of that, or 0.45 factor of that, that will be equal to delta T. So that is the correct answer. And the reasons for this you should know. In the case of octahedral, the number of ligands it will be more as compared to tetrahedral. In the case of tetrahedral, only 4 ligands, so less ligands present in tetrahedral. That is one of the reason why the splitting it will be less. Splitting it depends on the number of ligands. And the second one, the approach of the ligand, that is also important. In this figure even it is shown, so you can just consider this black points as the ligands of tetrahedral position, whereas this whitish one for octahedral. So the whitish one, or in the case of octahedral complex, the ligands they are approaching the d orbitals which are present over the metal ion in a straightaway manner, whereas in the case of tetrahedral from sideways. So therefore the splitting that depends between the interaction of d orbitals with the ligands, and that's how. So that is the second reason why delta O it will be more as compared to delta T. This one it is interesting question actually. Straight away this question it can be solved. What they have asked is essentially, in this complex MnH2O 6 times and MnCN6 3 minus, octahedral complexes of Mn3 plus, everything else it is same except for the ligand. So which is high spin complex, which is low spin complex? That fact they have asked. If you just know some basic idea that cyanide they are strong ligands, and with strong ligands always low spin complexes are preferred. Water, it is considered to be weak field ligand in VBT approach, and weak field complexes they form usually high spin complexes. From that fact easily it can be answered actually. Easily you can decide that MnCN6 it should be a low spin complex and MnH2O6 times it should be a high spin complex, and use the corresponding option you can choose. But because they have given the values, pairing energy, this P stands for pairing energy actually, and they have given the delta O, that is crystal field splitting of these two complexes. So based on this, how we can answer? Say in this case they have mentioned the complex. It is possible that say they can just say that a similar complex A and B, they are having similar geometry and say same oxidation state. Directly if they give delta O values and pairing energy, from that perspective also it should be possible for us to decide the correct answer. So how we can do that, we shall see. Right? See here the concept is that according to crystal field theory there will be splitting of d orbitals to T2G level and EG level. If this energy gap is high, that happens when the ligand is considered to be strong. If this energy gap is high, in that case, high in the sense if this energy gap it is more than the pairing energy, as it happens here delta O it is more than pairing energy. In that case, when you are filling electrons, because the pairing energy is less, in such case what happens is that when delta O is more, the filling it happens like 1, 2, 3, because the gap is more, pairing energy itself is less, pairing takes place, and that's how it results in low spin complex. This you must have studied, right? Whereas if delta O is less, if you consider this energy gap to be less, T2G EG energy gap it is less, in that case of course everything it is in comparison with pairing energy, because pairing energy is when pairing energy is more, delta O itself is less, it happens that 1, 2, 3. Now pairing energy is more, so therefore pairing it will not happen here. This energy gap being less, so the next electron it occupies here, EG level, right? So while filling the electrons of high spin as well as low spin complexes in accordance with this crystal field theory, definitely you must have done the exercise. The point to be remembered is that delta O when it is greater it results in low spin complex, delta O when it is less than pairing energy it results in high spin complex. So now if you just consider MnH2O6 times 3 plus delta O, it is given to be 21,000 for MnH2O6 times, it is less than 28,000. So when delta O is less, it is high spin complex, and for the other complex delta O it is given to be 38,500 centimeter inverse, which is more than 28,000. So therefore when delta O is more, it should be low spin complex. So corresponding option, when if you have decided correctly, you should choose here appropriately. So if you read here, both are low spin, cannot be the possibility. Here MnH2O is said to be low spin, and MnCN6 it is said to be high spin, not possible. MnH2O 6 times 3 plus is high spin, and MnCN6 3 minus is low spin complex, makes sense. Here both are high spin, which is not possibility. So therefore option C, MnH2O 6 times it is a high spin, and MnCN6 3 minus is a low spin complex. This will be the correct answer for the question. The next question, it is also based on coordination chemistry itself. All these are classic examples, and repeatedly questions will be asked related to this kind of species. So when this kind of questions comes from your practice, without doing anything, without thinking much, you should be able to decide the shape or geometry or say magnetic properties of a given species. But let's see how we can decide the magnetic property as well as geometry considerations according to valence bond theory, valence bond approach of these three complexes. So first we should know this fact. In fact actually VBT treatment it has no clear distinction between strong and weak field ligands, but for our convenience most of the times we treat the coordination chemistry of VBT complexes considering strong and weak field considerations. So according to that consideration, carbon monoxide as well as cyanide, they can be considered to be strong ligands, and Cl minus it is considered to be weak ligand, because this strong field ligand and weak field ligand actually it comes in crystal field theory, right? but we have just mixed up both, and this is very common practice that some ligands that are treated as strong ligands and some ligands that are treated as weak ligands in valence bond approach also. If we approach from that side, we should know this fact. Now if we consider nickel electronic configuration, this is nickel in elementary state, it is 3d8 and 4s2. Of course 4p vacant orbitals will be available, so this will be the electronic configuration. So now first NiCO4, you might be knowing it's a carbonyl compound where nickel it is in zero oxidation state, so this itself we can consider. And hybridization here to form NiCO4, because this carbon monoxide it is a strong ligand, we say that when the carbon monoxide ligands they approach, these electrons they pair up here, these two electrons they pair up here, and 4s it mixes up with 4p to form sp3 hybrid orbitals, and 4 pairs of electrons from carbon monoxide it will be occupied in these sp3 hybrid orbitals, and the final electronic structure it can be placed in this way. Now the point here is that it is sp3 hybridization, and because it is sp3 hybridization it should be tetrahedral in shape. They have not asked it, but the NiCO4 molecule it is tetrahedral in shape. Mainly we are interested in magnetic property. As we can see, all the electrons they are paired, so therefore NiCO4 this should be diamagnetic species. This is diamagnetic species. Now moving on to the next one, NiCN4 2-. Here basic fact, Ni it is in 2+ state, that I will not work out again. So that means these two electrons they will be removed first, and again same story happens. These two electrons they are removed, and it is approach of cyanide ligands, so these two electrons they pair up, and because these two electrons they pair up, so here one d orbital which is empty that will be available for hybridization, and that will mix up with this d orbital, s orbital, and 2 p orbitals. Out of 3 p orbitals available, 2 of them it will be involved in hybridization, so therefore it will be dsp2 hybridization. So here one p orbital it has become extra, this you don't consider, so it will be dsp2 hybridization and one empty 4p orbital. So now the electrons they will occupy here cyanide, it will be each cyanide ligand it will be giving one unpaired electron, 4 of them they will be occupied here. Here also the electrons occupied. Again final conclusion about the magnetic property, this is also diamagnetic itself. NiCN4 2-, it will be diamagnetic, and because it is dsp2 hybridization, we should know well that it should be square planar geometry for this. This is considered to be, or this is a square planar complex, NiCN4 2-. Lastly, we are left with NiCl4 2-. The difference here is that Ni2+ in both the cases, but here it is cyanide ligand, here it is chloride ligand. Chloride is considered to be weak. When we consider it as weak, so here these two electrons they will not be available in 2+ state. So in NiCl4 2-, so it will be Ni in 2+ state. So this 2 they will not be there in the beginning itself. So now these two they are present. Because these chloride ligands they are not strong ligands, there will not be pairing up process here. So this remains as it is. 3d orbitals they remain as it is. Remaining empty 4s as well as empty 4p, they will undergo hybridization to form sp3. And the 4 pairs of electrons from chloride they will be occupied here, because here the electrons they are not paired up, so therefore they will be occupying this itself. And now again it is sp3 hybridization. sp3 hybridization means it will be tetrahedral itself shape. But now if you look at 2 unpaired electrons they are available, because 2 unpaired electrons they are available, this species it will be paramagnetic in nature. To answer this question what we need is this information, right? So correspondingly it should be, this should be diamagnetic and this should be paramagnetic. So here what they say is that both are diamagnetic, so this cannot be the answer. NiCl4 2- and NiCN4 2- are diamagnetic, they say here, but we know that NiCl4 it has come out to be paramagnetic. NiCO4 and NiCN4 2- they are diamagnetic, yes, it is correct. NiCl4 2- is paramagnetic, yes, correct. Further you can just make sure that this is also wrong. NiCO4 is diamagnetic, and both of this they said that paramagnetic. No, NiCN4 as we have decided it is diamagnetic, so therefore this is also not the answer. So we can straight away go with option C. Option C is the correct answer for the question. The next question is from F block. the actual magnetic moment shows a large deviation from the magnetic moments calculated from the formula mu j is equal to g into square root of j into j plus 1 in the case of. So actually this formula it is used when the coupling of L and S it is more. In such case this formula it is to be used to calculate the or to predict the magnetic value or magnetic property, right? So of course we shall just move to the answer directly, and this is also fact that europium 3 plus it shows large deviation. Here it is not possible to calculate this and prove the fact. We should know this fact, but how the fact works that we shall see. Europium 3 plus it is F6 species, and the F electrons, if they are filled in 7 of the F orbitals, it will be occupied like this, and based on this if we can calculate S value for 6 unpaired electrons it comes to 3, and L value calculation say plus 3 plus 2 plus 1, so it happens to 3 plus 2 plus 1 6, and then here minus 1 and minus 2, so it's minus 3 plus 6 minus 3, so it will be overall 3, and J it is to be actually L minus S because it is less than half filled, so it will be 3 minus 3, it will be 0. So now from this J value if you go for calculation of mu J, so mu J it will come to 0 because J itself is 0. Of course this G Landis factor if you calculate it comes to close to 1, it can be calculated, but let's not go to that exercise here. But the mu J in this case it is 0, but the experimental value if you observe mu experimental actually it is 3.5 Bohr magnetron. So mu J whatever we have calculated it is totally different from mu experimental. So why it is so, that we should understand. First we should know when this formula can be used. As I mentioned earlier, this formula it is applied to calculate the or to predict the magnetic moment of lanthanide metal ions, because in most of the cases in the case of lanthanide ions the J value or the J coupling it will be dominant than the crystal field effects, and that's how this formula it works. But in the case of europium 3 plus complexes, the other reason, before moving to the europium 3 plus complex, we can even see that this formula it will be applicable when only ground state it is contributing to the magnetic moment, and as I mentioned earlier the coupling constant lambda it should be very large. In such scenario this formula it can be used, but in europium 3 plus there are some variations. In europium 3 plus as well as in samarium 2 plus, the easy to remember thing is that both are F6 systems. This value of lambda it is small, usually it will be in 1000 centimeter inverse order. Here it will be somewhere in few hundreds. That is the first reason. Because of that and along with that the other reason is that along with ground state even excited state it is populated at room temperature itself. So therefore there will be contribution from excited state also towards the magnetic moment. Because of these two reasons the experimental magnetic moment it will vary from whatever we calculated or whatever we have calculated from mu J. So therefore of course it's factual question. We should know that in these two species europium 3 plus and samarium 2 plus there will be deviation, and option C it is the correct answer. There are so many other aspects associated with the magnetic properties of these lanthanoids. It is not as straight away as in the case of D. So therefore we should know some of the other facts also regarding the magnetic moments of these lanthanoid ions, because straight away questions have been asked and there are all chances that in future also they'll ask questions related to this. Moving on to the next question. UV visible absorption bands of lanthanide ions are sharp because particular why they are sharp. So now if we just compare this UV visible absorption spectra of lanthanoids with our traditional D block species, in case of D block we know that usually we get this kind of broad peaks, and in the case of on the contrary in the case of lanthanoids it will be sharp like this. It's just representation. So now they are asking why it is so. So here you should be very specific. They are specifically asking you what is the reason of the sharpness of peak, whereas in the case of D orbitals the DD transitions they are broad. Why FF transitions they are sharp? That is the question, right? First thing is that in the case of lanthanide ions mainly the absorption spectrum it will be because of FF transitions. Now we can look at all the statements and carefully we can just decide what is the reason, exact reason for the sharpness. Why I am stressing this is because they have given some reasons here. All these reasons, they are correct. The statements whatever they have made here, they are correct. But the question is whether that statement, it is correct explanation of this sharp peaks or not. That is the question. So you cannot just go with any statement just thinking that the statement is correct. For example, spin orbit coupling is more than crystal field. Yes, usually it happens. Just as I mentioned while discussing the earlier question, spin orbit coupling, it is more than crystal field splitting. That's usual thing that we observe in the case of this lanthanoid complexes. But that is not the answer by the peaks they are sharp. Next, Laporte forbidden FF transitions. Yes, FF transitions, for that matter even DD transitions, they are Laporte forbidden. So that is not the reason. Of course, because of this forbidden FF transitions, the intensity, this absorption, it is less. As you can see here, it is less than DD. In the case of DD transition, some Laporte relaxation it will be observed. So here, even that relaxation it cannot be enjoyed. So that's how the FF transitions further they'll be weak. We usually say FF transitions, they are weak and sharp as compared to DD transitions. The next one, the transition 4FN to 5D1 type Laporte allowed. Yes, this is also fact. But these sharp transitions, they are not F to D transitions. Sharp transitions, whatever we observe usually in the case of this lanthanoids, they are because of this FF transitions itself. They are not F to D transitions. So that is also not the case. F shell is well shielded from the vibrations of ligand. Yes, this is the correct one. DD, they gain little intensity and they are broad because of the same reason. In the case of transition metal complexes, d orbitals, they are much exposed to the ligand environment because they are not buried inside. They are in the valence shell itself, or they are very close to valence shell. Because of that, the ligand vibrations that gives some kind of Laporte relaxation, and because of that the intensity it will be gained, and because of that vibrational phenomenon itself, the DD transitions they turn to broad. Whereas in the case of F orbitals, they will be buried inside, and because of that ligand vibrations, even if they are present, they will not affect the FF transitions. Because of that, FF transitions will be sharp and the intensity it will be less. Right? So this itself is reason for the both the properties of FF transitions, weakness as well as their sharpness. It is because of option D. So the D option, it is correct explanation of the question. So therefore option D is the answer for the question. Straight away question, next one, it is factual question, which is the Coleman reagent they have asked. Actually it is an organometallic compound, dioxane solvented NaFeCO4. So you can just work out the oxidation state of Fe here. Fe it is in minus oxidation state, Na it is plus, and overall this has to be minus, right? So CO4 it is neutral ligand, so therefore Fe it should be in minus oxidation state. So this reagent, sodium tetracarbonyl iron, that can be considered to be Coleman's reagent, and this can be prepared by reacting FeCO5 iron pentacarbonyl with sodium metal. So sodium metal, what it does is it donates 2 of the sodium atoms. They can give 2 electrons to Fe, and one of the CO it will be kicked out, and the reaction it will produce Na to FeCO4. So here I have missed 2. So here it should be 2 minus then, and if it is 2 minus, this should also be 2 minus charge. Yeah. So it will be this reagent form, which is not known as Coleman's reagent, and this is mainly used in the synthesis of aldehydes from alkyl halides. That's the application, and that's how the Coleman's reagent is important. And Na to FeCO4, the first option itself, right? So the other options, ruthenium and iodine complexes, whatever they have given, you can rule out them easily. You may have to decide between these two. If you know that it is only iron carbonyl with sodium salt or as sodium salt, you can easily answer that. It is option A. The next question, very interesting one. Which one of the following compounds will be most likely to undergo reductive elimination of ethane? Here, this phrase, it has a lot of importance. Most likely to undergo reductive elimination of ethane. It simply means that the reductive elimination possibility, it can be present in other complexes, but in which among these it is most likely to undergo reductive elimination with elimination of ethane. Both facts we should consider. Now, first we should know few conditions which favor reductive elimination of a complex. Usually, higher oxidation state of the metal and valence count of 18, valence electron count of 18. This is not followed that strictly. When in the example that I have discussed here, this is not followed. But usually, in reductive elimination, 18 electron complex, it will be converted to 16 electron complex. And very, very important one, leaving groups, they should be cis to each other. This reductive elimination, it is considered to be microscopic reversal of oxidative addition. In the case of oxidative addition, the product, whatever we get, whatever two groups we add, they will be cis to each other. So therefore, reversal of it, that should also be true. So therefore, reductive elimination, leaving groups, they should be cis to each other. That is very important. And in this particular question also, this third point, which is an important characteristic of reductive elimination, that plays very important role. So now, considering all these, we can look at the oxidation state. Based on oxidation state, if we can eliminate some of the options, that will be easy. So straight away I will write the oxidation state. I will not go for calculation. Vanadium, it is 2 plus because CH3, 2 CH3 ligands, 2 minus. And similarly here platinum, if you consider, it will be, in this case, it should be 4 plus because here overall there is plus charge and 3 CH3 groups. So CH3, it is considered to be minus group. So therefore this minus and 4 plus, overall it makes plus. So therefore 4 plus oxidation state is that. And in the case of option 4, it is 2 plus. As you can see here, only CH3, others are neutral ligands and no overall charge, 2 plus. And this one, I don't know like what is wrong with this. So number of ligands are also more, and phosphorus they have given. I doubt this should have been PT or some other metal, and readily it is possible that this is just option filler and this has got nothing to do with the questions. We may have to decide with these three. Just based on oxidation state itself, we can decide that this is the answer, because here it is PT 2 plus. Platinum, if you consider 4 plus higher oxidation state, that can be converted to 2 plus. Reductive elimination is possible, but 2 plus it is not possible. Just based on that, we can discard this option. And the other important thing, the third option or third point, if you consider here 3 methyl groups are present. When 3 methyl groups are present, if only 2 are present, there is possibility that 2 they can be trans to each other. Reductive elimination will not be possible. If 3 are there, definitely one of the group, it should be cis to the other given group. All the 3 we cannot keep them mutually trans. So that's how here it is most likely, because of oxidation state and because of 3 methyl groups, that 2 of the methyl groups they can be removed. Say you can easily consider these 2 which are cis to each other, they can be removed and they will form ethane. So that's how C2H6 or say CH3CH3 removal, it is most feasible in this case because of the trans orientation of 2 CH3 groups and because of 4 plus oxidation state. So now the oxidation state after reductive elimination, 4 plus 2, it changes to 2 plus. So therefore, if we consider this fact that the most likely to undergo reductive elimination of ethane, careful observation, it suggests that option C should be the correct answer, and option C itself is the correct answer for this. There are all chances that you can think that D could also be the possible answer, but no, because of these two considerations, oxidation state as well as cis orientation of CH3 groups to form ethane. So this is most favorable to undergo reductive elimination, and option C is the answer. The next one, again it is from organometallic. Which among the following beryllium alkyl compounds are stable? It's about stability, and in organometallic compounds of this kind, the stability mainly it will be due to beta hydride elimination. Compounds which can undergo beta hydride elimination, they will be unstable because they can undergo beta hydride elimination to give some other product. So now, whenever beta hydrogen it is not available, such complexes they will be stable. Now, if you look at this one, right, only one alpha carbon atom. So with respect to this is called as alpha. Alpha hydrogens are present, no beta carbons or beta positions itself. So this should be stable because beta hydrogens they are not available. If you consider here too, I have clearly shown one beta hydrogen, alpha and beta CH3 group, one hydrogen which is present as beta hydrogen that I have shown. So whenever beta hydrogen is present, so it is possible that say this bond, we can just show it in this manner also, right? So hydride, it comes to the metal with its electrons, and there will be formation of hydride bond with metal, and in turn this bond breaks because the electron requirement of beryllium, it has been satisfied, and that's how this bond it breaks, and this bond or these electrons which are available, they will form double bond here, and what happens is that, so this side it will be CH2, right? So the other way also similar thing it is possible, just one way we have shown. This is called as beta hydride elimination. Whenever beta hydrogens are present, that will be possible. Now if you consider the third complex, in this case also beta hydrogens they are present. So if you just expand C, it is attached 3 CH3 groups. So all CH3 groups they becomes beta to beryllium. So beta hydride elimination is possible here. So here if you consider fourth species, this should have been butyl everywhere, Bu plus they have made. In KSET such silly printing errors they'll be there, and we should understand, definitely they'll not give grace marks. This question is not given with any grace marks. This we should understand that it is butyl group. So now butyl group, but one more CH2 is present in addition. So now this is alpha, this is beta. This carbon, it does not directly attach itself to any of the hydrogen. It is attached to 3 methyl groups. So that's how beta hydrogens they are absent in this case. So therefore this one as well as this one, that's 1 and 4, which are devoid of beta hydrogens, they should be stable. 2 and 3, as I said, they can undergo easily beta hydride elimination, they'll be unstable. So now they have asked which of the following compounds are stable. So stable, it should be 1 and 4. So 1 and 4 you can look at. So 1 and 4 option A itself. Stable options, they are 1 and 4. 2 and 3 if you consider, they are actually unstable options, right? Option A is the answer for this. 19th question, again it is related to organometallic itself. Straight away one, among the following compounds, which one is not an example of zintyl ions? So even if you do not know what are zintyl ions, you can just see that A, B, C, they are of a kind. So SN9, Pb5, all metals as well as non-metals, say, or metalloids. In the polyanion form they are present. This is different. So just based on that also you can decide that this is not an example of zintyl ion. But let's understand what these zintyl ions are, some more aspects about zintyl ions. So zintyl phase, actually it is a phase when group 1 reactions like alkali metals, they, or even you can consider alkaline earth metals like calcium and all, when they form or when they react with a main group metal or metalloid, they form this zintyl phase. So zintyl phase means, like here just ionic form it is represented. So this can be sodium, 4 sodium ions, and SN9 4 minus. That is overall it is called as zintyl phase. How it is formed? It is zintyl phase. It is how it is formed, it is given here. So now zintyl phase contains cations, and cations here it is not shown. Cations along with that molecule like polyanions, only this part it is shown here, right? So when you add this zintyl phase into ammonia, liquid ammonia, or ethylene diamine, or even crown ether solutions. So in the case of crown ethers, we can expect the cation to be solvated, or even in the case of cryptands. In such situation, this anionic part it will separate. So this can be called as zintyl ion. So therefore, this also zintyl ion, this also zintyl ion, this also zintyl ion. Just option D, it is not the correct zintyl ion for this, right? So the answer for this is that it is this, which is not zintyl havas, so it is D, right? Yeah, as I mentioned, the molecule like polyanions, like this A, B, C, they are actually referred to as zintyl ions when it comes to ions. Or zintyl phase means along with this some cations they'll also be present. So option D is the answer for this. Last question. And yeah, some more. These zintyl ions, they are even called as clusters. Most of the times we call them as clusters because here like similar groups, they are bound to each other. That's how they are called as clusters. Let's move on to the last question. Half-thrown anion is isoelectronic with. I'm not sure whether this question is correct or not, because as per my knowledge, so like isoelectronic thing, it will not happen here in any way. But actually the behavior of this particular anion half-thrown, it will be similar to that of C5H5 minus, because the C5H5 minus, it can coordinate in eta 5 mode to the metal. In the similar way here, this species C2 B9H11 2 minus, so that can also give eta 5 mode, and that's how they are similar. But how they are isoelectronic, I really do not know. From all considerations I tried, but I could not make it out that these two are isoelectronic. If any one of you knows how this isoelectronicity of these two species can be proved, please let me know it in the comment section. Right, so looking at the length of the video, almost it is 1 hour video now, so I'm just considering 20 questions in each video, because I'm giving a very detailed approach. All the other related aspects, everything it is being discussed. So that's how keeping the length in mind. So this KSET-24 paper, it will be discussed in parts. So this will be the first part. If you are new to the channel, you can subscribe the channel, and you can share this video with your friends, and you can let your opinions know in the comment section. Thank you for watching this video. Thank you.